Brilliant. So today we're joined by Professor Nigel Cassidy and Dr. Paul Regan from Aquaspira and Birmingham University. I don't know if you're aware of it. The National Buried Infrastructure Facility down at Birmingham University has just been opened, and they've actually got Aquaspira in there doing this testing at the moment. And this year they won what's called the iICE award, which is an award for research innovation, looking at what can be done in the future, not necessarily a product on the market at the moment, but where we should be going, what we're doing. And this certainly is quite groundbreaking. And with that, I'll hand over to Paul and Nigel to present. If you can keep questions either on the chat message on the side or save to the end, we much appreciate, and keep mics on mute. Thank you. Bye.
Thanks, Sean. Good afternoon, everyone, and thank you for joining us today. Nigel and myself are going to talk you through a thing called SmartSense, a concept that we have been developing together. So just provide you a quick overview of the presentation. We're going to quickly touch on what SmartSense is and where it originated, the mechanical testing of the materials that we've carried out and how we've done that internally so far. We're going to also look at the product testing and linking it to the digital analysis that we are carrying out, the development of the digital twin and the BIM data that goes with all of this together. And basically, though we haven't produced a product yet, the intention is to provide something to the market that's off the shelf, that's called SmartSense, and we're going to just give you an idea of how far we are along that road to produce it. So every flexible pipe manufacturer knows that installation of the product is the most important consideration when using flexible pipes. BS 9295 highlights this fact with the incorporation of an installation control type, which provides an increased deflection percentage based on backfill material and competence of the installer. For the best installations, there is a requirement for supervision and for the use of S1 material. Now, sadly, with the increasing costs and the requirement to keep carbon emissions low or to eliminate them completely, there is a requirement to basically monitor these installations. Now, we think the answer is the use of technology, and that might provide the answer. By embedding sensors into the pipe, a pipe can be monitored without the need of an extra person attending site, and potentially the primary backfill around the pipe can be changed to something more sustainable, or we can use the as-dug material on site. Previous projects of this nature have used sensors that have just been glued onto the surface of a structure, such as using epoxy resin to basically glue strain gauges onto a pipe wall. We have gone one step further and we've embedded the sensors into the HDPE. The original idea was developed to monitor the installation of a pipe on site, but we soon realized that sensors could be used to do a lot more. So for instance, prior to the installation, to monitor if the pipes have been dropped or damaged on site, during the installation to monitor the stress and strains within the pipe, but also the compaction density around the pipe, and then after installation to continue to monitor the structure of the pipe and its local environment. Now, in 2021, the University of Birmingham and Aquaspira submitted a research proposal to Innovate UK, where we were successfully awarded £250,000 to complete the first step of making SmartSense a reality. So where did we start? Well, we first started by evaluating the raw materials and looking at our internal recycling streams. We looked at our use of HDPE and evaluated the internal recycling stream to make sure that the heat cycles that we put the materials through did not degrade beyond the point of what the virgin material we use to make the pipes do. And then secondly, we evaluated the steel that is encapsulated within our ribs. We checked the density of the recycled HDPE to make sure that it stayed within throughout the process the same as a recycled variant of it. And we also used a melt flow index machine to check the flow rate of the materials to see the different recycled material blends are still within specifications that we run internally. We then evaluated the mechanical strength of the HDPE and the steel components using our in-house tensile tester machine. So what that entails is testing the waterway wall seams, butt welding of the component parts, and the properties of the steel. And we basically looked at different blends and the properties of those materials to combine them together to give us the best mechanical properties for our pipes. And then finally, we evaluated the ring stiffness of a number of pipes, assessing the resistance to load and ascertaining their ring stiffness values. To do this, we used the method set out in BSEN ISO 9969, though this standard is not directly suitable for our product, but we lent on it. And during the part of the mechanical testing process, we changed and varied the test to see how different setups affected the ring stiffness values and looked at, in particular, at the elastic and yield point of our product. This information was used to evaluate our finite element models that we produced internally. Now, the graph on the screen shows 4 physical ring stiffness tests. These plots show the elastic and yield point of 4 unsupported pipes in a parallel flow test. The blue and purple plots show 2 finite element data sets. The blue plot accurately plots the yield point of the pipe but does not show the correct elastic behavior. The purple plot shows the opposite. The third iteration of the model will combine the 2 plots, providing a more realistic rheology, which will provide us the first digital twin of our product. Now, a number of sensors were embedded into our standard manufactured pipes. The picture on the screen at the moment shows the embedded fibre optic cables that run around the circumference of the pipe as well as longitudinally along the pipe. Now, these pipes were used in an above ground test at Embedment, and a below ground test, but Nigel will explain more about that now.
Okay, thank you very much, Paul. Good afternoon, everyone. I'll give you a quick run through about the testing we've done. And without going too much into the details, what we're trying to do is replicate some of the ring stiffness tests in principle. We'll also expand on that so that we can get very accurate data to help support, optimize, and ultimately ground truth or above ground truth the finite element models, the digital twins as they're developed. So for our above ground tests, which we completed a few months back, we take 2 sections of the pipe, put them together as an interface coupler, and basically do a 3-dimensional, if you want to call it, ground a stiffness check test by loading them in different deflections, different loads, and measuring the strain using fibre optics, strain gauges, and the displacement using linear transducers of the pipe as a whole. We also used some prisms to look at the 3-dimensional shape, and I'll move on to that in a bit. But the things with the test is we've created numbers of tests, different scenarios, either with a linear load, or if you look on the left-hand side of the digital model we have here, a cone load where the load is actually distributed amongst the segments and the ribs of the actual pipe itself, and that gives us a bit more control over the movement of the pipe, and we're looking at the 3-dimensional structure there. Got over 150 gigabytes of data on these tests alone, so we have very high resolution, high accuracy data that helps inform our digital models. Next one, please, Paul. So going through the sensors themselves, you can see the fibre optics. The green one is a dynamic fibre optic, which means that we can up to 10 hertz. We can actually measure the dynamic load stroke strain changes through the fibre optic. The rest either wrap circumferentially or longitudinally in patterns. It's a static fibre optic system that we do before, after, or during a test, and that gives us a snapshot of the strain at roughly centimetre resolution around the whole fibre optic, and that can give us microstrains down to around about 10 microstrain level. Next one, please. They're also complemented by load cells on the actuators, strain gauges into circumference on spring lines, invert, crown, haunch and shoulders, and also by linear transducers picking up the displacement of the pipe as we actually deflect it and load it. Typical loads are up to about 5-6 tons, a bit more than that, and our deflections around about 5% maximum, and typically in increments of about 1%. So you're looking at millimeter increments as the most finest resolution, up to about 90 to 100 mil of full deflection. Next one, please. And they're complemented by these prisms. This is with a company who does called BMO, who does tunneling research, and they want to move from prism-based measurements into fiber optics. So we piggybacked with them, and there are some really interesting results. And these prisms are able, with a total station, to map the three-dimensional displacement field, i.e. the position in the pipe, to 0.1 of a millimeter, about point plus or minus. And as we deflect the pipe and it moves both up and down and in its radial direction, linear direction, we're able to see the distribution of the actual pipe structure as we do the loading. Next one, please, Paul. So you can see here, you can see the prisms actually highlighted by the flash on the camera inside the pipe, the total station setup automatically controlled, and the setup of the above ground test in the National Buried Infrastructure in the far left corner. Those of you who've been there, had the pleasure to do that, you will see that we've developed this, and then we've got more and more testing in there. And this facility allows us to do this both digitally, because we can model it, but also as a physical ground test. And you can see the loading beams and all the data collection scenarios and equipment set up on the pipe. Next one, please. So to give you a little bit of example, Paul's going to flick through here. You can see the pipe being deflected around about 100 millish. And these are the results that we've got from the fiber optics and the strain. And you can see that the displacement of the pipe, as you would expect, it sort of flattens up a bit, but you can see the strain patterns around the pipe. And we're looking at around about 500 to 1,000 microstrain, both from the fiber optics and from the strain gauges, so they match well. And this gives us control and understanding of the nature of the stresses acting on the pipe and the strains distributed across it, so that we can then calibrate our digital twins. So when this goes into the ground, the results that we get, we're confident about, but also we can then tweak the digital twin to actually give us a very accurate representation of what goes in the ground. And as you can see from the flicking up and down there, the actual snapshots of strain and the dynamic strain tells us about the arrangement in the environment around the pipe itself, so the pipe is acting not only as a sensor for itself, but also as a sensor for its buried conditions. And that's where we're going with SmartSense. Okay, next one, please. So we take this to the next stage further, and this is literally what's happening in the buried infrastructure facility at the moment now. On your left-hand side there, you can see the hydraulic actuators, which are representing loads. We haven't tried to make it exactly like a railway line or exactly like a road, but we're actually trying to mimic the loading conditions so that we simulate a rail structure, a slab base, but also an axle weight for a lorry or a tram, so you can see the loading conditions on the pipe that's buried in the ground. And you can see the pipe situation has expanded in sort of concept. So you can see the long two sections of the pipe, and under the green tarpaulin sticking up, there's actually a chamber. It's an elbow. It's a 1.8 meter diameter pipe, and that elbow sticks above the ground, and that represents an access chamber. And we want to be able to see the stress strain relationships both on the pipe and on the structure. It's actually a manufactured structure. So we've got fiber optics and sensors. Next one, please, Paul. Wrapped around the whole system. You can see this photograph literally taken a couple of days ago. You can see we're setting up the static loads at the moment, and I was in there yesterday, actually doing vibrational loads, and we've got a digital twin version that we're calibrating at this moment in time. And poor resolution, but you can see the sensors that are wrapped around the pipe. We've got strain gauges and fiber optics, both dynamic and static. We've got load cells, and we also have some quite interesting scenarios with soil pressures, both below the loads and off the side. So where that legato block wall is, we've actually got soil pressure sensors indicating the soil pressures in the soil at the spring line and at the top, effectively the crown level. So we can see the distribution of stresses in the soil, the pressure distribution around the pipe at 1.52 meters away from the load and around the pipe as well. Next one, please, Paul. So give you a little bit of hint and of where we're going, and I think we've included these because I think this is really interesting to our PIG colleagues here about pipe installations. One of the things we're always concerned about is the pipe installed properly. What does it look like? How does it change? And can we then use the sensing, the SmartSense, to determine whether the backfill's been put in properly, or if there's a change in the future, what that change represents. So on the left-hand side here, you can see the preloaded conditions. So we filled basically to the bottom of the pipe, plonked the pipe in, and the pipe is just resting there, effectively under gravity. And the red circle you can see is its rest position, as you'd expect. It's gone a little bit oblate over its own weight, and the black circle would be the perfect conditions of the 1.8 meter diameter pipe. We've then filled it up, and we can see this in the green level. We've compacted to specific densities, and we've filled up to the inverge, and you can see that the pipe is sort of contracted in the center, as you'd expect, but pushed up at the top, and the strain gauges are measuring similar levels of strain as we saw with the above ground test, and those arrows that are shown on the picture, they represent the amplitude and the effective bending moment that those strain gauges are picking up. So if you have compressional strain, these are on the outside, they're pushing up outwards is the effective movement you would expect. We have linear displacement inside the pipe, and you can see the pipe's gone pretty much 11 mils expanded in the crown to invert, and about 4 mils retracted in the center, showing that as you bury and compact around it, the pipe will squidge, want for a better word. Thank you, Paul. Next one. So we're now moving on the fill, again, compacted fill, up to the 1.2 meter above the crown level, the sort of standard level we've set. And you can see the soil pressure sensors there. We've got around about 7 kPa above and below the pipe, interestingly, but also about 9 kPa at the extremities of the pipe wall, showing that the pressures, the soil pressures, the stresses are distributed around the pipe. The pipe is acting as an arching structure and pushing those pressures around. The stress field, as I like to call it, is distributed around the pipe. This is reflected in the strains. You can see the strains going up, and the pipe has obviously, as you'd expect, dropped, but not completely. We dropped about 6-7 mil, and it's now going into a more circular cross section, but we still have some non-oblate deformation in the pipe itself. The next set of tests is then we put the static load, which is effectively the slabs, and the actual bases of around about 450 kilograms across that footprint of the concrete, effectively replicating a slab load. And we can see that the pipe has rested back to its almost close to its ideal position. The soil pressures have gone up, doubled as you'd expect, but the strains have also distributed themselves around the pipe. And I think we find that quite interesting, that actually the soil pressures have dropped slightly, not too much, but the soil stress field has also altered. So we've got this complicated relationship between soil stress field and the pipe deformation. Next one, please, Paul. So that gives us where we are, and I would like to finally just really give you a nod to the future. Not only are we able to look at the compacted fill, test, check, see whether the stresses and the strains are all as we expect and are right for an installation, but the sensors also allow us to look into the pipe. And this is a little demo, this is a prototype we've got of a soil sediment sensor within the pipe. And this is sensing effectively the pressure of the soil, the sediment in the pipe as it fills up. And this is the next stage of where SmartSense will go. And we've sort of demonstrated this at a few events, and we've got quite a lot of traction for the water industry, Network Rail, because we're able to accurately, if you could just move it up, Paul, able to actually accurately determine the thickness of sediment lying in the pipe at centimetre levels. And our goal for the next stage is to develop this as part of the SmartSense product and bring that innovation in so that this can automatically determine whether your pipe's filling full of materials, and of course you've got the installation materials, and any perturbation in the stress strains on the pipe are then can be thought about by whether it's something in the pipe or outside the pipe affecting it. And that's where we're going with SmartSense in the next stage. Okay, hand back. Thank you, Paul.
Basically, that is it. So if anyone has any questions,
Okay,
I'm sure that we'd like to hear them.
Any questions of anybody? One from me while you're thinking. How scalable is the digital twin? So can you look at like different pipe diameters? Can you look at bad backfills?
In principle, yes. So it's really a case of computation. If you've got more computational capacity, you can scale it up significantly. We've got some supercomputing facilities where essentially you could put in a very, very large scale structure, which could be tens, hundreds of meters. It's really it's constrained only by the computational facilities. That's the future, and we haven't tested how well it will work, but in principle, yes.
One from Chris Kemp. Can this technology be applied to carbon steel pipelines, e.g. to monitor deflection under road rail crossings?
I'd say yes, from a technology point of view, you can do. I think the difficulty will come in, and maybe Paul could, is how you actually get those sensors embedded. One thing about embedding the sensors into the pipe is, when we worked a lot on this, is the HDPE is the same material. So when you embed either a strain sensor or other sensor, you know that the encapsulated sensor is actually representing the material properties of the pipe. If you had two different materials, and we've done this in the past in Embedment University, you're not really sure whether you're measuring the pipe change, and we want very fine changes, or you're measuring the change due to the nature of the two materials that are actually making that sensor installation, like the glue on the steel pipe or anything like that. So there is a complication there.
Ben's come along with, could this technology be applied to smaller scale pipes, e.g. 100 mil pipes on residential developments?
Paul could answer better, but yes.
It could do, yes. It's just a case of, instead of being internally to the pipe, it would more probably be welded externally onto the outside of it. I think that's the only kind of that I'd make at this stage based on what we've looked at. It's how you would actually apply the actual sensors to the pipe. And I think when you talk at 100s, 150, 225s, you're more probably looking at the external side of the pipe rather than the internal.
I was down at the buried infrastructure facility a couple of weeks ago myself, and I think the one thing to state is, actually, I think you're only just touching the boundaries of what the capability is on that kit there. There's things like movable floors below to simulate settlement. There's thrust walls you can push off. There's you can simulate frost heave with even the loading. I think you mentioned was it 450 ton you had on the side, but you can go up to, is it 2,500 ton?
Yeah, basically 2,500 kilonewtons. So we have a big static 250 ton actuator that we can use on structures. But I think the interesting is when we can go up to 25 ton on the dynamic actuators, so they can run up to about 10 hertz. And we've got 4 of those, so we can put multiple, basically vibrational stresses into any structure, either on the ground or below the ground. So we've got a lot of flexibility, and the kind of pictures that Paul showed there, we can fab up. So it's kind of mechanoed, so we can fab up any type of loading structure. So it could be an embankment, it could be a rail, but it could also be a set of piles in the ground. And we have had a lot of interest from people who are looking at the structure-soil interaction, and how importantly, how a lot of the infrastructure here, like the pipes and the cable ducts, actually interface with that.
Yeah, and I mean, the amount of work that the industry is doing at the moment on the high speed 2 diversion of services, I think if any of them realise what capability you've got there in terms of optimising the designs rather than over designing, they'd be jumping all over it. And hopefully they'll see from today what capability you've got there.
Yeah.
Someone said, how are the sensors connected between individual pipes?
The fibre optics are welded into the pipe, and then there's effectively a non-welded join across the interface. But in the future, what we would do is we would join the fibre optics up from the outside with a coupler, so they can be put in an installation. And it's the same with any of the sensors connected on the outside. Each component part will actually have a connected through system. And what we'd like to do in the future really is, and we're not the experts, we won't be, is develop the system so that you could have it as a compartmentalized modular system. So you might have one SmartSense bit connected in a system. You can put that in the point of interest, so you can engineer where you want the sensing and build those up into modular bits. And the idea is it'll all be wireless in the future, and you can come along and the data will effectively autonomously collect and self-record and self-transmit.
That was from Jonathan Starling. Another one from Kurt. Are the sensors also used to check if the joints are water silt tight?
They can be, yes. So you could have effectively pressure sensors, a bit like the sediment sensor, around the interface. And we've talked about this a lot, Paul, Neil and I, about how we can manage. So you can test the pressure on installation. And then ultimately, it's quite simple to actually do moisture content measurement sensing. So under the pipe where you may have a join that you're concerned about, you can actually put those sensors in to check whether that's the integrity of that stays the same over time. I think ultimately it isn't a case of, you know, what sensors we can put anything. It really is, what is the problem the sensor's trying to solve, and then using the concept to solve that problem in the most efficient way, both cost and technically. And we see that as where SmartSense is initially going and how the sensing does it. But there's a bit to go down the road yet before we can prove it, and hence the tests we've got above and below the ground.
In my mind, it's answering the questions we didn't even know we could ask.
Yeah,
it's all right sitting on the BS committees on the 9295s and coming up with all the theory. I think this is the first time I've actually seen capability to prove what that theory puts into practice. I think the other line I picked up when I was down there the other week was, isn't this there's nothing else like this in Europe, is there?
No, the facility is unique. We don't have anything of the same scale worldwide with the same capabilities. And the pit which we're in is a small part of it. It's 25 meters long, 5 meters deep, 10 meters wide. You know, if you got the money, and it does cost a lot of money to run it, you could actually test any structure in there and deform it in different ways. And I think you're absolutely right. You know, from small companies like all ourselves here on the meeting, you can actually innovate quite quickly. But as you said before the call, taking that technology to the construction contractors, consultants, and ultimately the clients is difficult. That's the barrier. And we're hoping that with the research we're doing here, the concept in the product, and when it hits the shelf, people come along and go, oh, I can see it. I can see where that will work. And they will try it. And they won't get into this barrier of standards stopping us. And that happens across the whole of the engineering industry. And ultimately, and the things we haven't really talked about is we're all committed to reduce the carbon footprint. And if we can reduce it in the materials in the pipe and reduce it in the backfill, but make the backfill, as Doug, but understand and be able to see and control the quality of that installation, we've nailed certainly 80% of the issues that we see in the future. And it's the installation which is the important thing. Good installations make good systems. Poor installations make poor systems. My personal opinion. I'm sure Paul and Neil and you guys there would actually agree.
Chris has just put a question up. Can the technology be used to firefight systems built from GRE/GRP material? We've seen fire water pipeline fail due to cracked pipes. This technology could help in identifying when and where these failures occur.
In principle, yes. The fibre optics, interesting, not only detect strain, they also actually detect temperature. So we have to temperature calibrate, which is fine. That's fairly easy. But if you think if the pipe's under a moderate degree of strain all the time, you suddenly get a leak, the temperature drops. And we've picked that up on other pipelines. And also pressure drops. Some of the sensors we've got, we use for sediment sensor, actually pick up pressure changes. And you can wrap that around the pipe. So if you have a leak, it picks up the pulse in pressure. So there are different ways of using the same sensor sets for different problems. Ultimately, you're picking up strain, stress, pressure, temperature, and moisture content in and around the pipe. So any combination of that could actually be used to solve those problems.
Yeah, I think Ben's just typing a question as we speak, which might hopefully pop up quickly as we're while he's doing that. I think there we go. Do some of the sensors, i.e. strain gauges, become less reliable over time and require replacing?
Ultimately, probably yes, but if you think all the testing equipment you generally will have in your laboratories, out in any situation, next time you get on a plane, it's 30 years old. Those strain gauges are testing whether the pressures and all the mechanical joints are working in the plane. So we have proven technologies. They do last. What we do is got to make sure when we engineer the next phase of this, we engineer it properly.
I think a lot of it comes actually down to the installation, doesn't it? If you get the installation right, and that's the bit we're most important. What is the current design life of the sensors is being asked there, which I think you've already answered in terms of we're talking 30 years in terms of aviation, aren't we? And it's the same technology. Yeah.
And it's down to us as engineers, both research and in production and manufacturing, to really go through the process, test it, work it out. It's interesting. One of the on the chat there is about some steel pipes being lined with HDPE. We found in the factory, again, Paul and I will tell much more about that, actually good quality installation in the factory, that modular build really does help us. And the fibre optics will last a long time when embedded into the plastics. They cost more. So there's a price point versus an application point. The fibre optics can do very fine strain measurements. So it's really a case of how much risk do you want to take in a critical part of the infrastructure against how much you want to pay to monitor and mitigate that risk. And we all know that's a balance. I think for me, and I'm speaking from a researcher who does a lot, I think it's getting that message across to the clients so they bring it down to the consultants who then propagate that down to the contractors so that we don't miss out on the opportunity because somebody's cut a funding budget.
Right, I think not many more questions coming in, so we draw it to a close there. Nigel, Paul, excellent talk. I think everyone can understand now why you got the Future Innovation Award for future product development. It's quite something else. We've got another talk coming on next Tuesday, which is the valve track from UIS. That'll be 12 o'clock in a week's time. On that, I'll draw the meeting to a close. Unless anybody else got anything else to say.
No, thank you very much.
Thank you.
Thank you. Cheers.